There's a very quick way to repeatedly differentiate using the product rule, y equals uv. If I wanted to find the nth differential, well, our dear friend Leibniz, who was a bit of a genius, worked this out, that it's a combination of the product rule and binomial expansion. So if I took my top line and I differentiated it, I'd get this line here, wouldn't I? U dv by dx and plus v du by dx. If I differentiated it again, I'd get this term here where I double differentiated the dv by dx, this term here where I double differentiated the du, so like the u term, and I'd get two terms in the middle, wouldn't I? Because I could differentiate the u first and then the v, and then I could do the v first and then the u. So I end up with 2. And if you differentiated that again, you'd probably start to see that I get the end ones where I've treble differentiated. But I could come in 2 ways into this. I get my 2 and 1, so I get 3 lots of that differential and 3 lots of this differential. And if I did it again, you'd probably see that I'd get my n ones again, but then I could get 4 lots of this, 4 into here, and I could get 6 here. And surprise, surprise, I think you might have noticed that these coefficients here are the n choose r coefficients of a binomial expansion. So what's that mean? Well, I could generalize it, couldn't I? If I wanted to differentiate that uv at n times, well, I'm going to have my 2 n ones, then I'm going to have an n choose 1 du by dx, and then the rest of the differentials are on there. And if I generalize it, I'm going to have an n choose r with r differentials of u and n minus r differentials of v. So is that useful? Yeah, let's have a look at one that we could do then. Okay, here we go. So y equals e to the x times sine of x. I want to find the fourth differential. So what am I going to do? Well, u equals that. I'm going to differentiate it 4 times, and unsurprisingly we get the same value all the way through if we're differentiating e to the x. And v equals sine of x, so I'm going to differentiate that 4 times. So I'm going to go sine cos, a negative sine, and negative cos back to positive sine. Okay, what am I going to do with those? Well, I'm just going to, next thing I do is just quickly get my fourth differential equation from Leibniz Theorem. Yep, so there it is as my binomial expansion with differentiation. What am I going to do next? Well, I'm going to substitute these values that I worked out into each of the terms. So here's my first term, is going to be e to the x, and the fourth differential, that's sine of x. Here I've got 4 lots of the first differential and the third differential. Here I've got 6 lots of the second differential, that should have a 2 there, and the second differential, 4 lots of the first differential, v, and the third differential of that, of u, and then I get the v, and I get the fourth differential of that. And hey presto, you might now see that I could collect up those terms. Well, how many sine terms have I got? I've got a sine here. They've all got e to the x, haven't they? I've got a negative 6 sine there, and I've got a positive 1 sine e sine x there. So that lot gives me a negative 4 lots of e to the sine x. And how many causes have I got? Well, I've got a negative 4 here, and I've got a positive 4 there, so I've got none of those, and therefore the whole thing simplifies down to that. And that was a lot quicker than differentiating it and differentiating it and differentiating it. So what do we do then to use this? Think of it as the shortcut as being like binomial differentiation. Set up your formula that you want to use like that. Remember your n choose r terms floating around here. So you're going to work out the differentials. In practice, what do? We work out the differentials for u and v, and then we substitute them into the Leibniz equation, and then we simplify. Easy peasy, lemon squeezy.